All right. Hello, everyone. I'm Ahmed Ali. I'm a PhD candidate at the University of Virginia. And today, I'm going to present my paper on derivative-free optimization of neural nets using local search. So let me give you some background information first. Traditionally, how you train a neural net right now is you use a stochastic gradient descent-based algorithm like ADAM, and then you combine it with backpropagation to backpropagate the error, and you iteratively use this in a loop, and you optimize the loss function and update the weights accordingly. We were working on some robotics problems, like research problems, and traditional approaches were not working for us, and we went off to create something that is kind of, I wouldn't say very new. As you will see, that local search is not a new algorithm per se, but it's being used right now in a new way. And we find that it works for us. So why would we want to use derivative-free optimization? First and foremost, the gradients or the derivatives that you may have can sometimes be uninformative. And I plucked this quote out from an OpenAI paper, and I'm going to read it out loud to you. And it says, "A large source of difficulty in reinforcement learning stems from the lack of informative gradients of policy performance." And you can review that paper. I've added the reference down there. Basically, it also creates another tool for anyone who wants to use a derivative-based or a derivative-free method. You have that option. So what is local search? Local search is a variant of random search. It partitions a search space into smaller bins, where each bin is ideally sized that is much smaller than the original pool size. So in our case, for example, we're working on a 5 million parameter convolutional neural network, and our search size or our bin size is only 25. So this means that at any given optimization step, we're not updating the 5 million parameters or the 5 million weights of the network. We're only updating 25 at a time. And naturally, you would think that it's going to be very slow to converge because you're only updating very small portions of the network at any given time. And another aspect that we're incorporating is something called score decay. At any given time, in order to get out of local minima, we decrease the value of the solution that we found so far by a fixed amount at every optimization step until you can get out of whatever minima that you're stuck in. So let us show you some experiments. We use the fashion MNIST dataset. It's a relatively new dataset based on the original MNIST, but as you can see here, it has much more challenging images and classes. So it has the same structure. It's 28 by 28 images, but it's much more representative of modern computer vision tasks. And for these experiments, we use the categorical cross entropy as a loss function. So performance-wise, in the red line here, this is stochastic gradient descent. And in the dotted blue line, we see the performance of local search. Now, the optimization step is given on the x-axis. So you can see that local search is much slower to converge than stochastic gradient descent. And we computed it to about 50x slower to reach the same convergence, same loss. But we also found out that local search is able to optimize the CNN down to a zero loss. And this is lower than what SGD was capable of. And for comparison, we also included random search. Random search, it means you completely swap the network every time from a distribution, or sample the network from a distribution. And you can see that random search doesn't work at all for this problem. Another thing we did is an evaluation study on the features of local search. So first, we tried to use local search without score decay. And this is given in the red dotted line here. And you can see that after some time, after some optimization steps, the performance really starts to plateau, meaning that the optimizer got stuck in some local minima that it wasn't able to get out of. So this really validates our intuition or our hypothesis on score decay. Next, we wanted to see if we expand the search into the entire search space, which turns it into global search. And you can see that global search actually diverges rather than converges. Now, another small-scale ablation study we did is on the size of that bin. So when we said that local search divides the search space into smaller partitions, we wanted to know what's the ideal size for that partition. And the one that we were using was 25, and this is the solid red line right here. And we doubled that number to 50, and it landed us with that blue dotted line, which is a higher curve, meaning that the optimizer is converging to a higher loss than with 25. And then we doubled that number again, and we got that black line here at 200, meaning performance is getting worse with each increase in the bin size. Okay, so if we're increasing is bad, let's just keep on decreasing. We halved the size from 25 to just 10 dimensions, and we found out that this actually doesn't improve the performance as well. So what this tells us is that there is some parabola there, and we have to optimize the number of search dimensions according to that parabola experimentally until we find some better way to do it. Another interesting thing we did is, what if we dispose completely of the loss function and we just use accuracy as a single training metric? We were able to train the network using accuracy without any loss function, and we got it up to 75% accuracy. Now, this is not as good as if you had a loss function, but it tells you that the task is still somewhat solvable. So if whatever task that you have does not have a loss or a representative loss function, you can go ahead and try to use something like this method, and maybe it will work for you. So what do we conclude out of all this? First is that we trained a relatively modern VGG-like architecture CNN using local search with a single candidate derivative-free optimization method. We find that local search, although it converged to a better loss eventually than SGD, it was still slower. It was still much slower than SGD, basically an order of magnitude. And then we found out that we do have need to use score decay to get out of local minima, and that it is possible to train a neural net on a relatively modern data set without a loss function. So where do we want to go from here? First, we recognize that there are needs for further studies to validate the use of local search in different domains. Specifically, we're working on robotics. This is what interests us. But there could be other domains as well to use and validate LS in. It's also important to understand how the architecture of the neural network affects the search behavior of local search. We were using here a convolutional neural net with a VGG-like architecture. What if we were using recurrent nets or LSTMs? Will that make them harder or easier to train? It would be an interesting question to answer. Finally, we think this could be an important tool or a valuable tool or alternative. Doesn't necessarily mean that we're going to swap away SGD, but it can help researchers who are struggling with SGD as we were right now. This was Ahmed Ali. I just wanted to, a shameless plug in here, I'm graduating in January, so I'm open for opportunities. And with that, I thank you so much. Any questions? Yes.
Can I put it for code?
Yes, absolutely. It's free.
Is it available for download?
It's available for download. If you read the paper, we have the link in there. Yes, sir.
your work is very, I think, it's quite somewhat similar to recently approach. They try to use evolution strategy to solve deep reinforcement learning.
Yes.
Instead of using like normal policy gradient, like macro prediction gradient optimization for deep, because normally you use deep neural network and the backend for the model. So normally so they also try to using evolution, using those genetic and those police optimization. So yeah, I think it's just a suggestion that you can compare with your evolution, because they also use
Yes, I agree with you. But what you were talking about is called multi-candidate derivative-free optimization. And the number of populations that were used in those experiments is in the hundreds. So if you have a robot, it cannot perform like 100 trials and then go on a single optimization step. It would be too costly. What we're working on here is single candidate derivative-free optimization. So what you need to do is just a single trial, and from there, this is your optimization step, and then you keep going. So it's basically costly in terms of number of inferences or number of evaluations that we have to do. Okay. All right. Thank you so much.